Hello there, everybody, and welcome. This is Professor Thea with you here today to talk to you about the Boltzmann Ensemble. This is lecture 9 of our Physical Chemistry for the Life Sciences series. So let me go ahead and share my screen and let's dive into the exciting world of Boltzmann. As usual, we have the lectures available for you. This will be available for you online. Boltzmann is a very interesting historical figure, and I've actually been to see his grave in Austria. Now, Boltzmann, well ahead of his time, because you have to remember he was operating the time when people were not really sure that molecules were a thing. And so when he had all these ideas about particles and how they could be behaving as individual pieces, people really thought he was nuts, to the point where he basically just had enough, and he eventually very sadly commits suicide. But many of his works are well regarded today, and he's well remembered as a very important person who laid the foundation for an awful lot of work. And then, of course, after the proof that atoms actually exist and a lot of the advances that came shortly thereafter, his work then became really important. So today we're going to talk about the Boltzmann factor, and this ties into the partition function. So we're going to discuss this in a little bit of a different way. We're going to consider something that I call the lattice peptides. So I'm going to just draw some peptides for you. Here I'm going to just start drawing these out. So just follow along for now. And I will explain what I'm doing. So we're going to need to have these kind of lattice peptides. I'm going to fill these in a little more, make them look a little more interesting. I think we'll do them a size 2 on these grids. So the idea of a lattice peptide is that it fits on a lattice, as you might have guessed from my pictures. 3, 4. So notice that the size of each of these is the same, but they have different configurations. That's the key thing here. Like that. And then we have the 1, 2, 3, 4, like so. Okay. Oh, it even makes a nice straight line. Great. Now we're gonna just keep track of the ends on these things because they're gonna have different ends. So I'm gonna now draw the atoms on these. So we're gonna need some colors here. Oh, it's nice to have a colorful thing. So we'll have a blue dot on one side. This one is going to be positively charged. And we'll have a blue dot. So these are all the same. Scribbling erases ink. Ink is removed when you scribble over it. Select undo. Okay, got it. I'm sorry. It looks like we cannot scribble. All right, there we go. Sorry, I'm still getting used to drawing with this stuff. So there is a researcher whose name is Ken Dill, and he's kind of famous for these lattice peptides. The reason why the peptides are so useful, as we'll see momentarily, is that you can calculate things about them exactly. And we'll see in a minute that we're going to make a scoring scheme about them. Okay, so the reason why we have these all colored is because we're going to need to keep track of which side is which. So the blue one will be positively charged and the red one will be negatively charged. And we'll also have some hydrophobic ones, which we'll put in this nice cheerful green color here. And so the idea is that these peptides have 4 points on them. Oh, did I make this one too short? Yeah, they should be one taller. All right, let's see. I'm gonna have to revise these ones. Sorry, guys. That's not to scale. I need to go back here and get the gray. 1, 2, 3, 4. Yeah, and then over 1, and then 1, 2, 3, 4. 1, 2. No, it's still too small. I didn't do it right. Okay, let me do it again. There'll be a dot there. 1, 2, 3, 4 segments. All right, now I got it right. And 1, 2, 3, and 4 segments like that. All right, it's a little close to this thing here. I think there are ways you can like select them and move them, but I have not quite discovered that just yet. All right, so if you don't have colors, that's fine. The key thing you're gonna need to differentiate as you're taking your notes is the positively charged and the negatively charged stuff. And then we're gonna have some dots in the middle. Oh, wait, did I do this wrong? Is this still wrong? Yeah, it is still wrong. 1, 2, 3, 4, because I made it 5 instead of 4. Jeez Louise. Okay. All right. This one. Okay. The size, as you might gather, 1, 2, 3, 4. 1, 2, 3, 5, 6. Okay, there's 1 segment, there's 2 segments, there's 3 segments, and the 4th one. All right, yep. 6. 1, 2. Okay, let me put the dots in. Okay, that should be 1, 2, 1, 2. There should be a dot there. Okay, yeah, like that. And this dot. Okay, so this should be. Oh, that's wrong. No, that's wrong. It's important to get it drawn correctly. 1, 2, and then we do 1, 2, 3, 4. Okay, like so. And then now this color green in the interior. And I have 1, 2. All right, let's pretend that one's the right length. All right. Okay. And then we have a blue dot at the top. It's taking a while to draw all this. Doesn't like my drawing skills. Okay. And that's how we draw that. And then we have 2 points in the interior here. Great. Now can we get back to this? 1, 2. 1, 2. All right. And this one also is very wrong. Erase this stuff and that. And 1, 2, 3, 4. And that, right, like that. Okay, and then we put a dot on the end, a red one over the arrow. Arrow's not pertinent to it. Okay, so this one actually is not exactly the correct length, but we're gonna pretend that it is. All right, can we use our imaginations a bit? Great. It's taking me too long to draw them. Okay, so the idea here is that we have these peptides. Okay, and so these little beads are representative of the peptides charges, right? So you're aware that in amino acids we have a positive side and we have the negative side. That's why it's called amino acid, right? Amino is positively charged and acids are negatively charged. And so, like things attract, so when we have a positive and a negative thing, so we're thinking about protein folding. And when we have positive things folded next to negative things, they're able to interact and have a nice interaction. And when they're not folded nicely, then they, well, we're going to look at the distribution of that. Okay, so we have a folded state here, and then we have all these unfolded states over here. It seems like sometimes this thing picks up and makes a nice straight line for me, and other times it doesn't help me at all. Okay, so now let me get to my usual pen color, which I think is this one. Is that right? Okay, so here we're going to have the C shape folded one. Here we're going to have the Z shape peptide. Here we have the L-shaped peptide. Here we have another L-shaped peptide. And here we have an I-shaped peptide. Okay, so these are all unfolded, and this one is folded. Unfolded. So you can't, right there. Okay, it's catching the zoom thing. All right, sorry. These ones are all the unfolded ones, the ones that are in here. Okay, so with this in mind, we want to then think about how much energy they have. So I just drew this interaction here. And now what we're going to do is we're going to take a look to see how much interaction energy these might have. So this will be our reference state. So this is our reference state. And now what we're going to do is we're going to calculate how much energy these are worth. So I'm going to start all the way here on the right. This is the completely unfolded one. Nothing is interacting with anything. So we're going to say that, all right, we're going to make up a points system for this. And we're going to then talk about how many points we've lost relative to the reference state. So there are no interactions. So here we're going to make a little table underneath. Okay, so this is going to be points. Okay, so this one gets 0 points because there are no interactions. All right, let's take a look at this one up here. Now, our next one has an interaction from here to here because they are near each other. So we're going to have one interaction times, we'll let our interaction energy be -2 equals -2. All right, so that's how many points this one's got. Now this one also, so these are sort of like a van der Waals interaction that any atom can be involved in. All right, so here we also have one interaction, right? So these are interacting like so. So this one will get the same score, 1 times -2 equals -2. All right, now let's look at this one. There's more interactions going on here. This one's got 2 interactions. So we're going to have 2 times -2 equals -4. All right, now on this fully folded one, we got quite a lot going on here. We got these cross reactions and these cross interactions going on, and we also have this interaction here. So we could account for this as 2 times -2 to account for the interactions, 2 times -2 plus a -3 interaction for this right here, because this is an electrostatic, plus a -3 interaction equals a -7. All right, so we see that this has the least amount of interactions. And this has the most amount of interactions, and the number of points that this one got is the most negative. I've done it with negatives on purpose because negatives really are the way that we write these things in free energy. So I'm trying to prime us for thinking about the free energy scale, because we'll be taking this on pretty soon. Now, the other thing we want to note is that in these two, that we have a kind of a degeneracy going on. In other words, both of these have the same amount of energy, and that's going to become something that's important. And this all is capturing features that happen in real proteins. All right, so the next thing we want to do is now we want to calculate how many points got lost. So let's come back over to, no, I don't need that. All right, points lost, which means how much worse off is it than the reference state. So we're gonna do like this. Which I kind of like having dark lines between these, so I think I'll do dark lines because I feel like it. All right, now this is the reference state, so and it's -7, so it hasn't lost any points because that's our reference state. Now going from -7 to -4, this has got a +3, so you might think that plus is good, but in free energy you want to have the biggest magnitude of negative number. Okay, you've got the most energy out. Okay, now these ones are both gonna be a +5. Okay, and this one is all the way up to +7. So this one is the worst. So let's just write out the rules for the lattice model, which I've kind of been describing to you already. I start my timer? I did not. All right. Sorry about that. Okay, so rules for the lattice model. The great thing about doing these kinds of things is that there are, in fact, actually rules. And that's what makes this so useful, because of course, in the real protein folding world, we cannot actually make such simple rules. So these are going to be, well, we get to have this little system where we get to make up all the rules. So it's -3 for electrostatic interaction between blue, which is our positively charged, and the negative red beads. Why is it decided that I did it for -3? Well, I just made it up and it's my world, so I can do whatever I want. So I'm gonna do -2 points. This is also points for van der Waals like interaction. That's when two beads are diagonal. Then what we do is we tally the points for each microstate. Now, this is a nice vocabulary word. What exactly does microstate mean? Well, microstate means those little states that I made for you. It means these different foldings is what we call a microstate. All right, so that's what we mean for that. So you see that we calculated the different number of points, set the most stable to 0. And I'm just writing these out for you, but we already did all of these. Set the 0 and ask how much less stable all the other states are. Microstates. The energy states are discrete because of the scoring system we made up, which is definitely not the case in real proteins. No, that's not. Spelling is important. In principle, energy can be obtained from solving the Schrodinger equation. But we saw how complicated the Schrodinger equation already got, even in systems that were pretty simple. That's why we don't necessarily solve things that way. All right, so next we're going to draw the potential energy diagram. That does not look like a D. All right, so what we want to do is we want to map out the microstates. So let's see, I'm gonna need 7 of these. 1, 2, 3, 4, 5, 6, 7. And I'm just gonna do an extra one just to be sure. It's gonna look kind of like this. 1, 2, 3, 4, 7. Yep, I miscounted the first time. Okay. So I had an extra 4, 7. All right, that's great. Now, so this is the potential energy on the y-axis. And what we're going to do here is we're going to now represent where the peptides fall on this. Okay, so the C peptide has the value of 0, right? So the C peptide, here we can draw these on maybe in a different color. Pink one out. Okay, so our C peptide is our reference state, and the C peptide height in the y-axis is the thing that's important, not no, the length of the bar. Okay, so this is our C peptide. This is the ground state. And now let's take a look. The next one up. So this one had 0. Now the next one up is at 3. Okay, so now we're going to draw a potential energy diagram by going to the 3. So we're sitting on top of the line. I'm drawing them like this. I mean, it really is just like the width of these doesn't mean anything. It's how far up it is that matters. But I need to give it some width so you can see it. So this will be, no, the Z is what I meant to write here. That doesn't really look like a Z. Okay, this is the Z peptide, which is the closest to the C peptide because we retain the van der Waals interactions. Okay, this is called our first excited state. You may recognize some of these kinds of words from spectroscopy, and that's because it has to do with where the electrons go. And now we go back up here and look at this. We now have these degenerate states where we have several peptides that both have a +5. So now I need to go to the +5 level and I need to draw these in. So we draw one, and now we have another one. So we're gonna make 1, 2, 3, 4, 5, 3, 4, 5. Yep. Okay, like so. This is the L1 peptide, and this is the L2. This is degenerate. Because there are two of them. And the final one is at +7, and we have one of them. This is the completely unfolded one. So this one goes up here. One is where we represent the, I'm going to just draw like this is the I peptide. So this is the first excited state. This is the second excited state. This is the third excited state. We talked about the Rydberg equation and the excitation of electrons between energy levels. It's sort of related to that. Okay, so what these bars mean is that there's a particular peptide at a particular energy. In other words, a microstate has an associated energy. And the other important thing to notice is that because the L1 and L2 peptides both have similar shapes, they have the same energy. And so this leads to degeneracy. This means we have two places at the second excited state, and that's going to have some implications. So now what we want to talk about is how many peptides would actually be in each state if you had an ensemble of peptides. It's going to depend on the energy that they have. So I'm thinking about a beaker. Yeah, okay, we'll draw the beaker like this. It's a beaker. A little spout, like so. And in the beaker is a bunch of peptides, okay? And there's water in the beaker, so we'll just put some blue highlights, okay? So we've got water in here. And inside the beaker, there are a bunch of peptides, and they're in these different states, but they might be interchanging back and forth between each other. So how many are in which state? Well, that's what we're bound to calculate today. So it's like that. So in other words, you kind of just like have a collection of them. So some of them are in the C shape. And so there's a couple of C's floating around in here. It's molecules, you can tell that, right? And we have some Z-shaped ones, and there's some L's. There's two kinds of L's, but they're kind of hard to tell apart. And they're all just, floating around in there. Oh, that one came apart, an L. And also there's some straight ones, but not as many because they have the hardest energy. Okay. So the big question is, how populated are each of the energy states? So intuitively, we probably have the idea that the ground state would have the most population, and the highest excited state, which has the most energy, is going to have the greatest instability or the least peptides in that conformation. And so that's exactly correct. But what if we actually wanted to be quantitative about this? That's just the surface of the water. So this is what we would like to do. Intuitively, we can say that the lower the energy, the more stable or the more probable it is going to be. And here's a beaker of lattice interchanging lattice peptides. This could also be thought of as an ensemble of them with many replicates, or it could be one system over time. You could really look at it in any of these ways. Can this be quantitated? Yes, but the quantitation is probabilistic. Yes, probabilities. So they are interchangeable, which is the really cool thing. So Boltzmann factor and the partition function Q can be used to help us with this. And because the Boltzmann factor has is usually represented as KBT, I often write Boltzmann with a beta to help us associate those things. And that's how I write function fxn, and it's called Q. All right, this is the above notes. Okay. Given a system, energy states, where are you going to get your energy states from? Well, that's why we just drew the energy diagram. E1, E2, E3. And so on. The probability that the system will be in the state is going to depend exponentially on the energy of the state. That pretty much sums it up. The probability that the system will be in state with J. This is energy with the subscript J. That is, of the various choices, we could index them. Depends exponentially on the energy of that state. So in other words, we're going to be using some exponentials. Now, I'm going to write these down. We don't want to be mixing up all the p's. So we talked about pressure, and we also had rho, which kind of looks like a p for density. This is going to be p for probability, which we want to be a different p. So I'm going to write this as a cursive p to indicate probability. All right, so we're going to have Pj is proportional to, now we've seen this symbol before, proportional to e to the negative ej over kBt. Now, what exactly is this? This is k subscript b times t. So let's write this stuff out. Okay, so P probability. J is the index. Alpha means proportional to. Proportional to, sort of like an equal sign, but not exactly that. Okay, now we also have this KB. So the lowercase k, and then it's KB like so. This is the Boltzmann constant. And it's equal to 1.987 2041 times 10 to the minus 3 kcal per mole Kelvin. They're both in the denominator. Kb is also equal to the real gas constant divided out by Avogadro's number. So we need to note some of these things. This. Now we've seen where the ideal gas constant came from. Hey, I just changed the tip. What's going on? Pick the eraser. Wrong color. This one. Okay, this is the ideal. Yes. Constant. So what approximation do you suppose he made? He probably made this assumption that we're working with ideal. Yes. Okay. This is Avogadro's number. And T is the temperature in kelvins. Temperature. And so let's just write out then what the term PJ means. PJ means then the probability of a particle J. And by a particle in this situation, we mean a peptide, lattice peptide. But it applies to other particles to be in an energetic state. Energetic state J. Energetic. So oh, it's strange. I'm screen sharing, but I don't have the green aura around the screen that I usually do. It says I'm screen sharing though, so I guess I am. This is not normalized though, so it's not a probability per se. It's the probability to be in each state, but the sum of the probabilities doesn't add up to 100%. That's why we have to do the partition function. Okay, note. These are the raw probabilities. These are the raw values. They are not normalized. This is why we need the partition function, which basically just divides them out, just like you would to normalize something. Okay. Let's write the PJs for the lattice model. Okay. PJ. All right, so these are really actually proportional, but I'm gonna put an equal sign for now because we need to calculate their values. Okay, so I'm gonna do it like this. PJ. Okay, we're gonna make a little table equals E to the negative EJ over KBT. And all this KBT, this whole thing is in the denominator. All right, so now what we're gonna do is we're gonna calculate this for the Z shape. All right, so P sub, so these would be indices, but instead of putting 1, 2, 3, I'm just gonna draw the symbol for the lattice shape. So this is for the C-shaped one, equals E to the negative EJ, so this is gonna be E sub C-shaped peptide over KBT equals E. Now, what is the energy for the lattice peptide? Well, this is the ground state, so it's gonna be 0. And we got a negative sign, 0 kcal per mole divided by kBT equals. All right, so notice that anything to the 0 power is 1 and we're multiplying by 0. So in this case, we already know it's just gonna be 0. And it's this will be 0 and this will be the ground state. So it's 1. Next, we're gonna say, okay, the probability for the Z-shaped peptide, remember that's the one that's kind of like that thing, we'll call it P sub Z, equals E to the negative E and then the Z-shaped peptide over KBT. That's a lowercase k, although it kind of doesn't look that way there, equals. Now, what was the amount in this one? This was negative 3 equals E to the negative 3 kcals per mole over, and notice that they're all going to be for KBT, so I'm just going to leave it like that. All right, and now we have the L's, and these are degenerate. So now we're going to have the P sub L1 equals E negative E sub L1 over KBT equals E to the negative, and the number of points that one had was 5. So this one is going to be 5 kcal per mole. Divided by KBT. And now we have the probability of L2 equals E to the negative E of L2 over KBT equals E to the negative. This will also be 5 kcal per mole divided by KBT. Notice that these are degenerate. Same values. Okay. And finally, we have that I-shaped one, probability of the straight one equals e to the negative E of the I-shaped peptide over KBT equals E to the negative, and this one was 7 kcal per mole divided by KBT. And so one could, in fact, actually substitute in all of the numbers to get those out. All right, so I actually did this on a spreadsheet to make this easier. And so I'm just gonna put the numbers over here for you, because we're not gonna worry about all that. Okay, so let's see. 0, 3, 5, 5, 7. Yes, so then we can calculate this out. Okay, so we got the number. So for the first one, it's 1. So the number is 1, and then this is 6.31 times 10 to the minus 3. And you can push the numbers through yourself. Hopefully you'll know about scientific notation, right? These are the exponents. 2.15 times 10 to the minus 4th. This is, and I'm being a little sloppy about not putting units. This is 7.35 times 10 to the minus 6. Okay. And also we'll have a few other notes. So KB equals 1.98720 times 10 to the minus 3 kcal mole. Okay, now what we're going to do is we're going to calculate for different temperatures. Say temperature equals 3000 Kelvin. Okay, well, what would that look like? These are peptides. We have the C shape. We have the Z shape. We have two L shapes. And we have the I shape, the linear one. And we have the EJ. Mole, which has the value of 0, 5, and 7. And now we have the PJ calculation. 1.0, 0.60, 0.3, 0.43, 0.31. And then what we would do is we would repeat this calculation. So we would want to do this with a variety of different temperatures. So for example, we could also do this. This is 30. 1 order of magnitude hotter. So now we're going to calculate the PJs again. This temperature. These PJs are at that temperature. Okay. For the C peptide, it's 1, 0.95, 0.92, 0.92, 0.89. Oh, and I skipped the 300 Kelvin. I'm gonna squeeze the 300 Kelvin in right here. I hope you won't be too upset. Okay, the cold. So basically we have cold, medium, and hot. All right, so here we have one. We have 6.31 times 10 to the minus 3. We have 2.15 to the minus 3. 2.15 times 10 to the minus 3. And we have 7.35 times 10 to the minus 6. Okay, so now we have our table at cold temperature, 300 Kelvin. This is about room temp, give or take, right? 298 Kelvin, about 300, around 60 degrees, 65 degrees, something like that. This is pretty warm and this is pretty hot. So this is a bit contrived because at 3000 Kelvin, a real protein would be vaporized, as would plastic. But whatever. Okay, so what we can do then is we can do a comparison of what would happen at various temperatures. I'm going to sketch a graph. J, at T equals 298 or 300. Yeah, let's say 300. It's basically, I mean, you're not going to see a major difference. Okay, so we have the numbers here, right? So the thing is that bar graph, right? Okay, so this is your energy. No, this is your, not your energy, this is your population. You have this, you have the Z, you have two L's, and you have the I. When you draw, okay, when you plot this, no, that's not right. Right, this should read 1. Okay, this is like your population. Okay, this one is almost 100%. I mean, for all intents and purposes, this bar totally dominates. And just look at the order of magnitude that we had here. Hey, if you look at the order of magnitude that we had here, these are teeny numbers. 6.31 times 10 to the minus 3. You move this 0.3 places to the left. So you're at 0.006, right? That's pretty small. So this is, for all intents and purposes, 100%. And like your bars are so tiny that you can't even see them, right? Because there's like no population. So in other words, at cold temperatures, everything is in the ground state. Okay, and that's what your graph would look like, and that's what the numbers show. So what we haven't done is we have not made the partition function. So what we need to do is normalize So it's like taking in, so it's like when you normalize anything, you'd sum the parts, the contributing factors. And then divide by that. Okay, Q is the partition function. This is the sum of all the microstates. In other words, Q equals the summation from I equals 1 to n microstates. E sub, oh yeah, J. It's J. Okay. So in our case would be E sub C peptide plus E sub Z peptide plus E sub L. Looks like a Pinocchio one. E sub L1 plus E sub L2 plus E sub straight peptide is what our summation would be. This is the partition function. So in other words, basically, we're just going to divide out by the total. That's what's happening here. And so we can take all these numbers and we can divide them out by their total. So we just take these numbers that we have here and we sum them up. So do you see that basically in the cold temperature, you're going to sum these up and it's basically going to be just the sum of the first one because none of these others really are adding much to the total. You're going to add 1 plus 6.31 times 10 to the minus 3 right now. How much is that? It's 1.006 plus 0.002 plus another 0.002, and now this one is way out in the 10 to the minus 6. The decimal equivalents are teeny. Okay, so this is your dominant one. But the interesting thing is that as you add more and more heat, so as the temperature goes up, notice that the numbers that you're summing, oh, some of these are getting a little closer to 1. So your bottom number always stays the same. This means the ground state is always accessible. But now look at this. I mean, these ones actually now almost all contribute. So, I mean, all right, let's just do a back of the envelope calculation. This thing pretty much sums up to about 1 if I summed over the whole column, right? That one's a little bit more than 1. This one is going to sum up to, well, among friends, you might say that each of these is almost 1. So this one is going to sum up to about 5. So our partition function is going to be a little less than 5 and a little more than 1 here. So when we divide these out by their various, well, when we put it into the E sub j over q, you see what's going to happen is it's going to be divided out by this new denominator number. So if we were to do that, what we would see is that in this case, the ground state is only going to be about 1/5 of the total, whereas over here, the ground state is going to totally dominate because it's the biggest number out of 1. I mean, it's almost 1 out of 1. The reason why it's not exactly 1 out of 1 is because you have these minor contributions from these other things. But as the temperature gets hotter and hotter, the effect it has is to drive up the probability that it's going to be in a different state. And so we can calculate. So what we would need to do is calculate Q's for each of these, and then by summing them up, and then we would put each of these values over that Q. And when we do that and make the graph, we get something that looks more like this. Okay, So what we're gonna do is we're gonna calculate E sub this over Q. We're gonna calculate E sub C over Q. We're gonna calculate E sub L over Q for each of them, all right? E sub 2 over Q. They're gonna have the same number. And then we'll have the E sub straight also over Q. Calculate each of these. Here is the sum. Okay, and it needs to be done by temperature. Okay. When we do this and plot it, let's take a look at what our bar graph is going to look like. J bipolar by substate various temps. Okay, so we're gonna do a cold, medium, and hot. All right, and here's 1.00. 1. Okay. So in the cold temperature here, I'll just pick a different, let's pick this for cold. We already talked about the cold temperature. It's gonna look like this. This is the dominant peptide. 1, 2, 3, 4. All right, and then we're gonna have the Z peptide. 1, 2, 3, 4. We're gonna have the L. 2, 3, 4. We're gonna have another L. And then we're gonna have the 1, 2, 3, 4. We're gonna have the linear peptide. Okay, so in the cold temps, it looks like this. And these are so low you can't even see them. I mean, these are even less. They're teeny. Okay, this color. Cold. 300 Kelvin cold. Relatively speaking, it's like room temp. Okay, then we'll have medium. So what color would we like for medium? How about green? What's halfway between blue and red? I don't know. White, gray. I don't know. Doesn't really matter. Let's pick another color. We'll do, oh, no, we do have gray. All right, we'll do gray. Great. Okay, so the medium temperature, this will be medium temperature. This is gonna be 3,000. This is medium. All right. The ground state is still accessible at 1. But what happens is these start to grow in. Now this one is going to be around halfway up. Now I can provide you with the quantitative ones of these. But for now, I'm going to just draw it schematically. It looks like this. These two are going to be the same. And this one is gonna be down here, about like so. All right. Then in the hot temperature, I'm gonna do in red, which is really a pink here. T equals temperature. Something very interesting happens. This still has the same number. Okay, so this says probability to be in this one is still the same. The PJ value is still the same. But what happens is the other ones grow in. And they're all about the same. So what this has some very interesting implications. That was weird. Okay. That doesn't actually mean anything. Okay. These are all the same. Yeah. Connected together, all the same at one. So we have some lessons we need to do from this. When the temperature is low, temp about room temp, the most stable state dominates. This is the most populous state. As the temperature rises, the probabilities shift. The higher energy populated it's become accessible and populated. And the limit high temperature, all states are about equally populated. And that's because they become accessible to from the temperature. And that makes intuitive sense because as you add energy into something, like if you are trying to throw a ball into a basketball hoop that goes higher and higher up, you need to throw it really high. But if you didn't have very much energy, you would only be able to get it into a lower one. But if you had lots of energy, you could reach a higher one. All right, so some important things about the partition function. The partition function can be used to write the ensemble properties. The ensemble property means the property of a collection of particles, such as the beaker lattice peptides. You might also be interested in the average ensemble energy. This is the angle brackets, and this means average. All right, we're going to have a little bit of calculus. D, that does not really look like part sign. Let me try that again. D, ln, that's natural log Q. And then the things that go down here are the things that are held constant. Or we could also write another definition. So there are two definitions. So the first one is with respect to the partition function to the Boltzmann constant. And this one is with respect to temperature. We can also write the heat capacity. C sub V. No, that doesn't look very good. All right, let me write it like C sub V. This is heat capacity at constant volume. The change in the average energy over temperature at constant N and V. You should have commas in it. Is equal to du dt and v. Subscripts and partial derivatives are for the parameter, are for things held constant. Things held constant. Right, so this is a partial derivatives, right? These are partial derivatives. Now, this is C sub V. So this also is saying what's constant. This is heat capacity. And constant is what this means. This is internal energy. Okay, so what is heat capacity? C sub V is a measure of how the energy of the system changes with respect to T when N and V are constant. So how can we use the C sub V formula? U equals 3 this is an equation for the internal energy. Okay, we have C sub B equals U over D E. And this is the heat capacity formula, which is given. Now, what we're going to do is we're going to do a little substitution here. So I have my eye on this right here and this U right there. Is an equivalency, and I'm thinking about plugging in. So now we're going to substitute in. So I'm going to write C sub B equals D over dt. All right, now we're going to be able to switch to d's because we're getting rid of the partials of 3r over 2 times temperature. I'm going to write it like this. I'll show you in a second. D dt. In other words, the reason why I've written it like this is because this is the variable. Oh, maybe that's a bit confusing because it's not the same as the other one. So let me just pick a different color here for you. I'll pick green. So this here is, so I don't confuse it with this. It's not the same as that. This is the variable. And how do I know that? Because it's d dt. That's why t is special, because I'm taking the derivative with respect to t. So I wanted to pull the variable out. And why did I say that? And that's because it's d dt right here. Okay, and that's why I wrote it that sort of a special way. And that's how I knew it was the variable. Okay, and so what I've done here is I basically just subbed in u of t. Now we need to take the derivative. So C sub v equals 3r over 2. Take the derivative. And that's what you get. Very nice. And that just breaks down into that very simple formula. Okay. Average pressure. So the angle brackets mean average. Okay. So we would take the prescribed derivative as we just did for the C sub v formula. And this is how you can do it. All right, well, that is basically the major things that we need to discuss about the Boltzmann ensemble. I will write out some additional information for you, or provide you with the actual spreadsheet where I did all the calculations. Oh, wait, hold on, hold on 1 second. We have some other things we need to talk about. We need to talk about what it means to be in the Boltzmann regime. All right, if the number of awfully quick, if the number of quantum states or molecular configurations or molecular microstates is larger than the number of particles then it seems that any two systems would be unlikely to be in the same state. So you have two peptides and you have 5 microstates. So just considering the number of peptides and the number of states, you'd conclude that it's 1/5 times 1/5 is 1/25 probability that they would both be, say, in the Z shape. So that would be highly unlikely. So let's just say, you have 2 peptides. And 5 microstates. The number of peptides and disregarding energy. Which isn't correct. You would conclude that it might do something like 1/5 times 1/5 equals 1/25 probability. They would both be in the same substate. Like, say, Z shape. However, many molecules are in the same state, especially the lower energy ones. By this we mean same microstate. C, Z, L, L, or I, for example. Especially especially the low energy ones. Why does this happen? This is because many of the states are inaccessible at a given temperature. Yeah, I should be calling these microstates really, many of the microstates. A given temperature, especially a low temperature. So for the lattice model, this one state called C dominates. So contrary to what we might have gotten if we just did multiplication out by just regular probabilities, we explore here. To plane not using energy. Some states are highly likely. And it's the energy that's important. Side. We can apply this to protein folding. So of course that's just a lattice peptide, but this actually makes sense for real proteins as well, which we cannot actually calculate exactly. So we might have some potential energy like so, and then we might have some position. Now let's just be realistic here and understand that we cannot really draw the multidimensional potential energy diagrams. And the reason for that is because they would be very high dimensionality and we cannot draw that. All right, so just some important things are the energy levels are going across like so, and we have this grid paper, so it's kind of helpful, but so, oh yeah. Yeah, let me draw it closer to the diagram I have here. This thing, this one. Okay, it's supposed to go back up. Okay. So what I want to be true is like Just making some markers on here. All right, so we want like that. These are just some different energy levels, which are not totally to scale, but these are energy levels, by the way. And this down here is the global minimum. It's very stable. All right, and these are all the energy levels. So let's see what the implications for protein folding we can glean from taking a look at the lattice peptides. Low temperature, proteins are folded. Just like when in the lattice peptide, we had a low temperature, we favored the C conformation, which was the quote folded protein. So the same thing is true for real proteins. As the temperature increases, what happens? Other conformations of the protein are explored. See, it unfolds. And this is fairly intuitive, right? So this shows like some partially unfolded substates, and this is your folded proteins. This would just be. So in other words, proteins don't like to be too hot, and this is why. Although there may be many states. Many substates. They're not all accessible at all temps. When the energy of the state is much greater than kBT, it is effectively inaccessible. In terms of statistics. Does not mean it's impossible, it's just highly unlikely to do so. So the Boltzmann regime tests if the number of accessible states greater than the number of particles use this formula. N over the H grade AN DT with 3/2. There's your Boltzmann regime test. All right, so today we have talked about Boltzmann equation. All right, so, and we've learned about the Boltzmann ensemble. And we've done this mainly working up a simple lattice model where we made up some rules for how we were going to calculate this so that we could calculate everything up. And the reason why we did this is because real proteins are much more complicated and don't reside on a lattice, and it's really hard to tell what their actual interaction energies are. But we could make this lattice peptide to make a sample of a protein and understand how it behaves. So we actually worked this up for this system, and we had this reference state, which is our folded protein, which we defined as having something like van der Waals interactions. And we also had these electrostatic interactions, which became important because we declared what was happening with the charged beads. And then we also looked at a number of unfolded ones, which were represented by these possible configurations. And this, by the way, represents all possible configurations you could draw for this. So we drew them all out and we calculated all of this up. So we made up this point system, and we also looked at the number of points lost, which told us its status relative to the ground state. And we've also written out the rules of the lattice model right here, which are basically as I just described, and each of these conformations is referred to as a microstate. So what we did next is we drew the potential energy diagram, and we noticed that L1 and L2 are degenerate. And we ask questions about how populated each of the states are when you consider, for example, an ensemble of interchanging conformations. And so we saw that we couldn't just simply do regular statistics by just saying, okay, like there are 5 substates, so it should be like 1/5 in each, right? That's not actually true. And so a couple of things play into this, and we need to calculate this using the exponential. So the probability of being in a substate is proportional to the exponential. This was the important work that Boltzmann did, and as the EJ over KBT is basically the equation for that. And we can substitute into this to actually compute it out. And we did that for a couple of samples and did leave a few for you to do at home. And when we worked this out for various temperatures, what we saw was a curious thing. At the cold temperatures, all the population is just in a single peptide. But we need to actually normalize the numbers here because these are not normalized. And that's what the partition function is all about. The partition function is really just the denominator. It's the sum of all the probabilities so that you can, well, it's the sum of all the raw count calculation that you get from using Boltzmann's equation, but you need to divide it out by the total. And when the contributions are really tiny, as they are in the cold temperatures, basically there's a dominant substate, and which is the C substate. It's going to be your most stable one. And as you increase the temperature, basically the populations grow to fill all of the different substates, which we can see by then doing out the division simply by the partition function, which I've shown here. Now, I didn't actually divide all of them out for you, but you can see that basically in the case we worked out, you'd be dividing by 1 here. In this case, you'd be dividing by 5. So these are going to work out to be all about equally probable, and these are going to work out that the ground state dominates. And when we make the graph, that's exactly what we see. We have that in the cold temperatures, which are the blue ones, that we have a dominant state, the folded one, and as the temperature increases, the substates grow in. so that now the ground state, well, the ground state is always accessible, but the other substates start to grow in and to have some appreciable population proportional to their energies, which we were able to calculate with the bead model. So when the temperature is cold, we have a single stable substate, and as the temperature increases, then we have the ability to grow into some of the other conformational substates. And we can also compute some important properties when we know what the partition function is. And we did a little bit of calculus here to see what some of those are. So the average energy and the heat capacity. You can also calculate the average pressure. So we also talked about what it means to be in the Boltzmann regime, and how this is going to play into the protein folding. So in protein folding, what this is going to mean is that basically the conformational substates are much more complicated. But when you have the ground state and the temperature is cold, the protein will be folded. But as you increase the temperature, the protein will unfold because lots of conformational substates become accessible, which makes a lot of sense with what we know about proteins. But we wouldn't have been able to do that explicitly for a particular protein because it would have been much too complicated and it's not on a grid. So that's why we did it with the lattice model. And here is our test to see if something is in the Boltzmann regime. Alrighty, well then, I hope that you enjoyed learning about the proteins and the Boltzmann ensemble and how to calculate the partition function. It's a very useful thing and means that now we're able to quantitatively look at what some of these things actually mean for proteins. All right, well, thanks so much for joining us. We'll have more to say about Boltzmann and thermodynamics and many other exciting things coming up. So I hope that you'll stay tuned and join us again next time for some more discussions of physical chemistry. See you later.